Well, here are a list of the 5 names I had over here. We have Blake, Ian, Lauren, Craig, and Vince. So what I have here is the graduating, the group of students who graduating. So we need to do an exit exam and exit survey, exit exam. So these 5 are taking 422. And I see Craig and Vince is here. So I really want to do it in person. I have 2 choices. I just get a opinion. We want to do it in person or do it on Canvas.
Well,
I will give you like 4 hours of time in next 2 weeks, so you can work on the exit exam and exit survey. You need to complete that before the end of the semester.
well, for some reason, I looked on my my what do you call it, Griffin GPS, and it said that my exit exam had been finished, but I don't remember doing it, so I don't know why it says so.
Yeah, we need to do a survey and yeah, just do it next week. But my question is, want to do it in person? We get together, or we just do it online on Canvas? So you can pick up because we have 5. Some of our students are not in Shenzhou. Ian is working out of state, if I remember correctly. Ian is working, and Blake is doing online all the time. I didn't say Blake. So my current plan is do it on Canvas. So I will work on those problems, put it on Canvas, and give it to every one of you 5. Give this test, and you do it online. Yeah, how if that works?
That'll work with me.
Okay. How about Craig?
Yeah, that's fine. So
It just
you
means
said you'd give it online?
yeah, that's like a midterm or final. You just do extra. This one is also open book. You can do it. The only limit is time limit. I give you, for example, 3 hour or 4 hour. Generally, it doesn't take that long. I just look at the exam. It's only 55 multiple choice. So I would think, you know, no more than 1 hour is needed. All right, that's I will work on this after class. Put a exit exam, and you also need to do the exit survey. Both I'll have both too on Canvas. All right, that's one thing we're going to talk about. Now we will move back to our main topic. So we are trying to study this transmission line. So we want to study this because it's a huge, big money involved, a lot of money, and our life depend on it. So that's why it's so many people put out so many times analyze this. So this is what going to happen. On the left, we have a generator or alternator, which will create millions or gigawatts of power. And that power will go through a transformer, go through a circuit breaker. That is for protection. You don't want anything overload your power line or overload your generator or transformer. So they have a circuit breaker. It's the exact same circuit breaker. The only difference is it will be the size of your house. Again, unlike the circuit breaker we had in our basement. I have a couple of circuit breakers, but yeah, those circuit breakers are huge. We will look at the pictures of those circuit breakers. And after the circuit breaker, we go to the tower. Those are the transmission lines made of aluminum and steel. The current it carries is in the thousands. For example, the voltage is also in the hundreds of thousands. So the voltage is up to 1 million, very high voltage. The current is in the hundreds and thousands of amps, hundreds of amps or thousands of amps. That is a transmission line. And what happens when lightning strikes? When lightning strikes, amazingly, 20,000 amps of current. So we have a short burst of huge amount of water dumped into, if you think about water as a current, so we got like a normal flow. All of a sudden we have a big flow dumped to the transmission line. How big? 10 times, at least 10 or 20 times the amount of normal flow. That will create a huge problem. So it will create a shocking on both sides. It creates a shock. Lasted about a microsecond, 50 microseconds. So from start to finish, 50 microseconds. If you talk about distance, we're talking about 20 miles. So 20 mile left, 20 mile right. And they travel at the speed of light. Very close. They travel very close to the speed of light. Not the same speed as speed light. The reason is it will be slowed down by all the capacitance and inductance. So it's a little bit slower, but it travels, for example, half the speed of light on both directions. So 20 times amount of flow, the current, up to 20 times. How about voltage? Voltage is also double. So normal current is so that's the amount of current, 20. So obviously we're causing damage. So we need a protection. The protection is arresters. So the arresters will be a special type of device. What are those arresters made of? They are made of a special component called varistors. My goodness. Varistors. Let me show you what are the arresters, surge arresters made of. So the surge arresters are made of Oh, these are what the surge arresters are made of. They are called varistors. Varistors. Is an electronic component. The electrical resistance varies with applied voltage. Yeah, that's a perfect device to protect our electronic equipment from lightning, for example. That is the surge protector if you have one around your house. I have a couple. Some of the plug-in adapters have surge protectors. So they have this varistors inside. Basically, it is a big resistance. Normally, it's a big resistance, so it's acted as open. But when the surge comes, if it will create a short, The short will obviously divert energy instead of going back to causing damage to your electronics. It will divert energy to the ground. So surge protectors.
So that's another name for the lightning arrestor.
Yeah, that will be your surge protectors made of varistors. Varistors. So we just have a big one over here. In your house, you will have a small one. They all made of same material. When the voltage here, when the pressure is too high, it's like the pressure relief valve. Mechanically, it acted as a pressure relief valve. In normal pressure, it's shut off. When the pressure is too high, it opened up. So all the pressure, extra pressure will be released to the ground. So you got protected on the other side. So basically the electronics is very much like a plumbing. Every equipment have a analogy to the plumbing system. So right here we have a pressure relief valve. So all those extra pressure will be released. Both directions. Obviously, on the other side, you need the same thing. And this is how we can create the lightning artificially. This is 4 million watts. It will create 400 kilojoules of energy. It will deliver that through lightning. So that's a big show. Basically, you have a flashover, and you create a loud and bright flashing through the two connection, through air, actually, through air. Have you went to a science museum? I went to this science museum in Chicago. So I highly recommend everybody went to Chicago, go to that, what's the name of the museum? Museum of Science and Industry, right? In Chicago. Museum of Science and Industry. There they have one of those. Right at the entrance, when you enter the museum, they have a big show every hour. Basically, you waited over there, and then you create a lightning show. Very impressive. Also, I have a little YouTube video. I just watched it. I felt it's really fascinating. So let me show you that YouTube video. So this is a little YouTube video. This is
Check this out. I'm going to show you how I afforded this car. Okay, you ready? All right, $118 for car insurance.
This is a so-called Tesla coil, but a very small one. It generates a high frequency, high voltage inside of the main coil, and that ionizes the air at the end of the copper wire, and the air will glow due to the created arcs. Depending on the Tesla coil power, the voltage arcs could get bigger. This project is very cool to look at, but not just that, it could also wirelessly transport power for some sort of devices, like for example this small neon light, or a compact fluorescent lamp like this one. As you can see, even if we don't have wires connected to the light bulb, it will still light up, because this circuit could generate very high voltage, in order of thousands of volts, and that could excite the fluorescent material inside of the light bulb. So how does this Tesla coil works and creates these high voltages? In this video we'll cover the main theory about Tesla coils and see a few schematics and examples as well. Be careful working with high voltages, because those could hurt you. Make sure that you subscribe and activate the notification bell. A huge thank you to all my patrons for supporting my work as well. So let's get started.
So if you're interested, you can continue watch it after class. Tesla coil, basically you can create that very dangerous high voltage, quite a show. It just to create that flashing, tiny little flashes with that little Tesla coil. Instead of these big ones. So if you're interested, you can do a little research on that high voltage. So once the voltage is high, it became dangerous. Also, it became some strange behavior happens. All right, any questions before we move forward to mathematics? So today we are going to talk about mathematics. So if we don't have questions, let's move on to today's main topic. Today's main topic will be, we're trying to analyze this transmission line. So the transmission line can be simplified like what we have in figure 16. So right on the left, you have a power supply. On the right, you have your customers. And that's another simplification. So the transmission line is very complicated. In real world, it's so complicated. In order to analyze this complicated real world problem, the only way to do it is build a simplified mathematical model. So with experience, with good exercise, we can potentially build a simplified equivalent mathematical model of a transmission line. So right here, figure 14 is a simplified, very realistic mathematical model for a transmission line. Of course, it's not the real thing. It's a simplified. That means when we analyze the real transmission line using this simplified mathematical model, we might have errors compared with the real world. If the model is built correctly, the error is, for example, less than 5%. That is all we wanted. So that will be an excellent mathematical model. So we are using a simplified mathematical model trying to understand the complicated real world. That is what we always do, because otherwise it will be out of control. The complexity of real world is out of control. And the only way we can handle is simplify. So simplify is a key word, simplify. Of course, with the simplification, we will introduce errors. Fortunately, those errors are less than a certain percent. So we still have a pretty good understanding of real world, even though we simplified. So section 19, we will start with theoretical or mathematical analysis of 4 scenarios. Actually 5. The author covered 5 different scenarios. So scenario number 1, we will talk about a resistive transmission line. Scenario number 2, we'll talk about the inductive transmission line. Scenario number 3, we'll talk about the inductive transmission line with compensation. That's very close to the real. Scenario number 5, we'll talk about inductive line plus resistive line with compensation. That's actually very close to the real world. The author didn't put it there, but I will add number 5, means inductive line with resistance, because in real world, the transmission line still has resistance. So that will be the inductive plus resistance. Number 5. Number 4 will be the inductive line connecting 2 large power grid. For example, we can have state KCPL. On the opposite side, we have a St. Louis PL. So KCPL and the St. Louis PL, those are the 2 power grid, and they are interconnected. So we'll talk about what happens if we interconnect 2 large systems, KCPL and St. Louis PL, what will happen. So that is today's main topic. So let's do the topic number 1. So this is a simplified transmission line. On the left, we have power. On the right, we have load. In the middle, we have a resistor. That resistor represents, for example, 100 miles of transmission line. So 100 miles transmission line with all those complex equipment, circuit breakers, all simplified to 1 resistor. So let's study what will happen. So this is what will happen. So when your customer change resistance from 0 to infinite, so the customer is all the customers of the utility company combined. You can have a 1 million customer. All those 1 million customer is simplified as a single resistor. So all the hundreds of miles of lines simplified as 1 resistor. Is that a good mathematical model? No, it's not a good mathematical model at all, but it's a good place to get started. So a good place to get started. So when your customer change from 0 to infinite, resistance change from 0 to infinite, this is the amount of power delivered to the customer. So we noticed if the voltage is 50% of the input voltage, we will deliver maximum amount of power. This has a name. It's called the maximum power transfer theorem. So the scenario number 1 is not what happens in the power grid, but it's a good starting point. It's called the maximum power transfer theorem. That means the maximum power will be delivered to the load if the voltage on the load is 50%. So what is other 50%? Other 50% on the R. So 50% on the transmission line 50% on the load, and then we have maximum power delivered to the load. So this is the equation, mathematical equation to calculate maximum amount of power. We basically, the voltage square divided by 4 multiply resistance. And that is the first scenario. So the author gave an example. If the source voltage is 1000, the transmission line voltage is 10 ohm, the maximum amount of power is 25 kilowatts. Scenario number 1, very simple. But it's not what happens in the real world. So we need a better model. So what is the better model? The second one. The second one is a inductive line. It's closer to the real world. So the transmission line has resistance, but it has more inductance, it turned out. So this is closer to the real thing happening in the real world. So on the left, we have power. On the right, we have customer. In the middle, we have a coil, inductive reactance. So here's what happens. When the customer change from 0 to infinite resistance, customer resistance change from 0 to infinite, the power 0 in the middle and go back to 0. So the power delivered at 0 ohm and the infinite ohm will always be 0 watts. So the power delivered will be 0 watts. That the horizontal is power, the vertical is voltage. At 70%, 70% of voltage, 70% of voltage on the load, we have maximum power delivered. So 70% of pressure. So if the pressure of the power supply is 100 or 1000, so let's do an example. If the voltage is 1000, the reactance is 10, how much power can be delivered? 50 kilowatts. So right here, 50 kilowatts. So the maximum will be 50 kilowatts. So I really like the graph on the figure 32. So this is a scenario number 1, 10 ohm resistive transmission line. The maximum power is 25 kilowatts. The second scenario is a 10 ohm inductive transmission line. The maximum power delivered will be 50 kilowatts at 70% of voltage, 70%. How about the next one? So this is close, but we need to improve. The improvement is the third one, called the compensated inductive line. What do we mean compensation? Compensation means we put capacitors on both sides. So we have a capacitor on the left and a capacitor on the right. So we put 2 capacitors, one on the left, one on the right, on both sides. The author analyzed using 1 capacitor, but generally we put 2 capacitors. 1 capacitor on the left and 1 capacitor on the right. What happens is, if we match this, here is a keyword. If we match the capacitor perfectly to the load, that's the keyword. If we match the capacitor perfectly to the load, then that's what happens. When we vary the resistance on the load, here's what happens. The power delivered will gradually increase. And then the power delivered will be maximized once we reach a certain resistance here. So once resistance reach a certain resistance, then we will have all the power, maximum power delivered to the load. Not only maximum power delivered to load, also 100% of voltage delivered to the load. So you have 1000, the voltage on the load is 1000. That will be a perfect scenario. So this will be a mathematical model for a real transmission line, very close, very close. So if I put it over here, it will be this line. So if we, this is the inductive transmission line. If we compensate inductive transmission line with capacitors, potentially we can double the amount of power delivered. Not only we can double the power delivered to the load, we also can have 100% voltage delivered to the load. So to summarize, resistive, inductive, and inductive with compensations. The last will be the really real-world scenario is number 5. Well, in real world, not only we have inductance, we also have resistance. So the last example, the author put it there, is a transmission line with 9.8 inductance and 2 ohm resistance, and compensated with a capacitor. What will be the power delivered? So this will be the dotted line, number 5. So the difference is only, instead of 100 kilowatts, only 80 kilowatts can be delivered to the load. Why 80 kilowatts? What happens to the other 20 kilowatts? It is lost on the transmission line. There's a resistance on transmission line. So you will encounter energy loss. That's the number 5 will be really close to the real world. So what happens is your customer resistance can change, whatever you want it, as long as we match the capacitors to the load, we will always deliver different amount of power, anywhere from 0 to 80 kilowatts. That's maximum power delivered. So the power delivered will be anywhere from 0 to 80 kilowatts. 80 kilowatts is maximum power delivered if the power supply is 100 watts. And perfect voltage, that means the voltage is always 1000 on the load. So the load voltage will always be 1000. And maximum delivered power will be 80 kilowatts. The author also put another analyze is in the real world, we want the load voltage don't have to be 100%. We call 5% voltage regulation. That means the voltage can go above and below 5%. So once we take that into account, for example, we can have voltage drop of 5%. So if we take that into account, 5%, that means right here, the voltage drop is right here. So what is the amount of power can be delivered? Number 1 scenario, only 4 kilowatts. Number 2 scenario, 30 kilowatts. 30 kilowatts instead of 50. Number 3 scenario, 100 kilowatts. Number 3 scenario. Number 4 scenario, 100 kilowatts. Number 5 scenario, 80 kilowatts. So does that tell you how good how important this capacitor is? So in order to have that performance, the important part is have a matching capacitor right there. This matching capacitor, sometimes even it has to be an inductor. So you have to have a matching capacitor or inductor right there. So you always have the voltage and the power delivered to your load. So you have to have a variable inductor or variable capacitor right there. So that is the excellent mathematical model. Number 5 is a perfect, is an excellent mathematical model to study transmission line. And all the real world practice is guided by this particular model. So that's a theory. It can be hard to understand at the beginning. What I really recommend is the author did an excellent job of explaining this complicated subject using simple terms. So excellent. The only way to do it is study scenario number 1, number 2, number 3, number 5. So we have 1, 2, 3, 5, 4 scenarios. And number 5 is really very close to the real world. So the conclusion, you can do all the math analysis. What is the conclusion? Conclusion is the power line are more inductive than resistive. So the biggest problem to limit the power delivery is this, X. So if you look at the X, the maximum power can be transmitted theoretically. The maximum power can be delivered is limited, of course, by the resistance, but more importantly, by the reactance. Right? So let's do an example. A typical reactance is about 0.5 ohm per kilometer. So if we have 400 kilometer is about the distance from Kansas City to St. Louis. So if we want to deliver power from Kansas City to St. Louis, what is the total reactance? 200 ohms. What is the maximum power can be delivered if we use a 8000 K high voltage delivery line? So we put the math together, it will be 3 gigawatts. So maximum amount of power can be delivered. Current technology is 3 gigawatts. That's the maximum amount of power can be delivered. In reality, you will add a resistor there, which will be 20%, 80% of the theoretical. So you multiply that by 80%, that will be more realistic maximum power potentially can be delivered to your customer. So on one side, you have your power source. The power voltage is 800K, 800,000. So if you have 800,000 and the inductance is 200 ohm here, 200 ohm, the resistance may be 20, 30 ohm. That is the total resistance, or 40 ohm. So you have 200 ohm inductance, 40 ohm resistance, and then you have your customer on the left side. What is the maximum amount of power the customer can get from this scenario? 3 gigawatts. That is implies you have to always match the customer with this. You see here is a variable. You have a slash line across that capacitor. That means that capacitor is not fixed. That capacitor have to be adjusted to your customer in real time. That capacitor have to be adjusted in real time.
Well, wait, what does that mean exactly? To adjust that in real time?
That
Like,
means
how do you do that?
That means this. It's called VAR compensator. So on the high voltage delivery line, you have to have a VAR compensator on both sides. That's another one. This one is a inductor. This one is the inductor. So you have to put a inductor or a capacitor to put it at both ends to compensate. So the power will be delivered as we want it. So you always have to have put a variable to match the load, because here's the challenge. Your customer is not fixed. Your customer change every second, every minute. So in order to deliver the power with the right voltage and the right amount of power, you have to compensate with a inductor or with a capacitor. So here is a big inductor, one on each phase. On each phase. Let's read a little bit about this. This is made of inductive reactors, figure 37. Inductive reactors. It can be fixed or variable. Variable obviously is even better because you want to adjust the amount of inductance needed with your customer. It will be a large coil placed inside a tank, immersed in oil. Intense magnetic force develop across the air gaps. It will oscillate 120 Hertz. So this inductor will be under tremendous mechanical force, is 120 Hertz. So the coil must be firmly secured to limit the noise to acceptable level. So it will be very loud, 120 Hertz noise if you, even though you secure them very firmly, it will still be the biggest 120 Hertz speaker you ever heard. If you're close to it, you will hear it, 120 Hertz. It's in this case, we do not want to create noise, but unfortunately, it's it's impossible to completely. So it's pretty loud, 120 Hertz. It's kind of like a 120 Hertz speaker right there in the field. So that's the inductive reactors. In most cases, we need the inductive reactors because the customer can shut off. So if the customer is shut off, we need to put inductors to make it to make the voltage constant, to make the power flows smoothly to the customer. So that's the inductive reactors. In some certain scenarios, if we, this is underload, if the customer is underload, what about the customer overload? So all of a sudden, everybody turned on their air conditioner, everybody turned on their furnace, everybody turned on their appliances. That's called overload. When overload happens, you need capacitors. You need capacitors attached. So not enough capacitor, you need capacitors. In that case, you have to attach a capacitor. So this compensator can be both inductor and capacitor. So this is another example, figure 39. This will provide compensation for both inductor when you underload, capacitor when you overload. So there is a perfect load. The perfect load called SIL. SIL is a perfect load. That means there's no capacitor or no inductor is needed. So on one side, you need an inductor to compensate. On the other side, you have a capacitor. But what if you have a perfect load? The perfect load called SIL. SIL. Under perfect load, you don't need any compensation. But it just, all your customer will be perfect, provide perfect resistance to your power grid. Obviously, that will translate to 40 ohm per phase, 400 ohm per phase. So typical power grid, a perfect customer means 400 ohm. 400 ohm customer. But your customer will never be 400 ohm. It will be either 800 ohm, that means underload, 800 ohm, or 200 ohm, that may be overload. So when you underload or overload, you need compensation. When you have a perfect customer, you don't need compensation. Anyway, this equipment will just dynamically vary the VARs to compensate, so to make the transmission line function properly all the time. In this type, you just compensate for underload compensation. Some power grid, they never overload or seldom overload. Very commonly is underload, so that's why they put inductors to make that compensation. Here is a picture of two transmission lines. How do we reduce inductance? Through practice and through research, we can reduce as much as 40% of inductance. Reduce 40% inductance. How can we do it? By using a bundled conductors. By using a bundled conductor. So what is that bundled conductor? If you look closer, this airy line is not a single line, actually a bundled 4 wires. So a more closer look at that bundled conductor is at the beginning of the chapter. Let me show you. Yeah, right there. Beginning of chapter, this guy is working on bundled conductors. 4 connectors separated 457 millimeter apart. That bundled conductor will reduce the inductance 40%. By reduce the inductance, it will capable of transmitting more power to the destination. So basically, you need a transmission line. You need reduce the inductance, also reduce the resistance, obviously. And you need a high voltage all the way to 800,000. You need compensators on both sides, compensators. That compensator, if it's an underload, the compensator will be inductors. If you overload, the compensator will be capacitors to keep the voltage in check. Otherwise, the voltage will jump up. The author did an example right here. If we do not have compensation, what happens? Let's do an example. If we don't have compensation, with no compensation, oh, here's the example. So without the compensation, the source voltage is 400K. Without compensation in this scenario, the destination voltage will be 600K. So obviously, that's trouble. On the left, you enter 400K voltage. On the destination, the voltage became 600. So you need compensation. How much compensation you need? In this time, you need the inductor compensate 1,000 ohm inductor. So once you attach 1,000 ohm inductor, the voltage drop to 400. So that gives you a extreme example where you need a extreme underload. How much extreme? There's no load, zero load attached to the customer. So all your customer is cut off. So that's an extreme scenario. All your customer is cut off from the power. In that extreme example, the destination voltage became 600. It's way above, it's very dangerous, dangerously above the 400. So in that extreme example, you need the extreme compensation. That extreme compensation is a 1,000 ohm of inductor attached to it. With that compensation, and your voltage will be dropped to 400 again. Of course, that's an extreme scenario. In a normal scenario, there's somewhere in between, and that is the extreme underload scenario. So in that underload scenario, you need coils. These are the 3 big coils to make that under control. Of course, ideally, you not only want inductance, you also want capacitance. That will be the compensators called VAR compensators. So it called VAR because it provides VAR. It provides a positive VAR and a negative VAR. Positive VAR means inductive VAR. Negative VAR means capacitive VAR. So basically, it means it can be either capacitor or inductor. So to make that transmission line work as designed, that means deliver the voltage and deliver power. All right, that's all we want to cover for today. A lot of theory, a lot of mathematical models. How many? 4 mathematical models. The last one, number 5, will be the closest.
So quite a lot here.
Yes, I hope your brain is not hurting right now, everybody.
It's a little stuffed, but I don't know. It'd be a lot easier to grasp the stuff if we could actually like see it happen in front of us. Like with maybe there's like videos where I could like watch this stuff happen with actual equipment and someone measuring it or whatever.
Yes, I agree. Yes. Do a simulation. Yeah.
Would so like something on like multi-sim?
Yeah, that's multi-sim. That's a good suggestion. I mean, if I have time, I will experiment simulation. A lot of graduates works in this area. Like I said, almost 40 of our graduates works in this industry.
Okay.
They build substations, they design substations, they maintain transmission lines. And they actually came back to us, gave presentations. Every year they come back, they want more of our graduates. They gave a presentation to what they were working on to attract our students interested in working for them. The company is Black & Veatch in Kansas City.
That's cool.
Yeah.
Man. I mean, I already got my job, so hopefully that's my job for a very long time. But we'll see.
Yeah, that's another good I think majority of them are electronics major. Potentially can manufacturing too, because we study the same amount. The courses, the reason they hire so many of graduates is because well, there are many reasons. One small reason may be 422, because we talk about transmission, power grid, generators. Not a lot of school talk about it. So when they coming back, they always refer to this class 422, because 422 cover this practical subject. Of course, when they go to Black-Ridge, they learn so much extra, because what I covered here is only a tip of the iceberg. And when you practical in the industry, in the field, there's so many real world knowledge. Obviously, those some of the graduates are doing very well in Black-Ridge. That's why they want more for graduates, because they felt the value of our graduates.
That's good. Okay.
It all started about 10 years ago. They started hire graduates. I still remember the names of the first 3 graduates they hired. One girl, a guy. Yeah. And then it snowballed to the current. 1 year, they almost hired a whole graduating class, like 10 graduates, they hire everybody.
Really? So, I was going to ask about the that test, because I went on my my Griffin GPS. Is that the test on here that says the university exit exam?
I'm not sure. It's department exit exam. Maybe it's also called university exam. I'm not sure. Just do it again. Doesn't matter.
Okay.
If you haven't do it, you have to do it.
Okay.
I will work on this to put it on Canvas, because in the old days, everybody offered in person, but I want to make it on Canvas to make it more flexible online. Everybody talking about put it online, but I will just do it. So put it
Yeah,
online. Maybe in the future, we will always offer this exam online instead of in person.
So it's pretty much over anything that we've done throughout the last 4 years, or 2 years for me.
Yeah, it's open book exam. You can have all the books, all the internet you want to.
Okay.
It's simple exam.
Okay. All right.
It's not on your GPA. It's not change your GPA, but it's still record for department. It's not on your transcript or anything, but it's required. Required for your graduation. Everybody have to do it.
All right. Sounds good.
All right. Anything else?
That's all I got.
If nothing else, I'll see you guys Wednesday.